Let's continue our case study of a solution phase reaction that is bimolecular. And this time we're going to look at the enthalpy change on going from reactants up to transition state. So delta H double dagger. So to do this, we're going to rewrite our expression for K for this situation. Remember we said that the rate constant was equal to Kt over Planck's constant times the standard concentration times e to the negative delta G double dagger over RT. And we just remind ourselves that we can always split delta G into an enthalpy component and an entropy component. Okay, and this is true if the pressure is constant and we're not changing the pressure here. So if we split that off, we could split that off in there. So we could say that delta, put that in there. So we can say K is equal to Kt over Hc e to the minus delta G, well, delta G we said was delta H minus T delta S. And these are, of course, activation enthalpies and activation entropies. The rate constant could be expressed using an Arrhenius formulation. Or we could say the log of the rate constant is the log of the Arrhenius pre-exponential factor minus EA over RT. And that can give us a handle on what a different definition of activation energy in terms of derivative of the log of the rate constant. So if we take the derivative of the log of the rate constant with respect to temperature, we can see, well, this is constant, okay, and then we take the derivative of this with respect to T, we get minus EA over RT. Well, this is a negative exponent, so we get a positive EA over RT squared. Or we can say the activation energy could be defined as the derivative of the log of the rate constant with temperature times RT squared. So we have the derivative of the log of the rate constant with respect to temperature times RT squared is equal to the activation energy. Okay, we can use this relationship because we can find this derivative using our Eyring equation formulation. So we said K is equal to Kt over Hc e to the negative delta G double dagger, which we could say is also delta H minus T delta S double dagger, all over RT. So let's take the log of K and then take the derivative and then compare the expression we get to this. So over here on the left-hand side we have Arrhenius equation. Over here we've got the Eyring equation, and we're going to combine them to see if we can develop a relationship between activation energy and activation enthalpy. Okay, so the log of K is equal to, we can start splitting this up here. So we're going to have the log of Kt over Hc, and then we have the log of this, which is just going to be minus delta H double dagger over RT. If we distribute that minus sign, we get a positive delta S double dagger over R, because the factors of T cancel. Okay, so let's take the derivative of this with respect to temperature. Derivative of the log of K with respect to temperature. So in this first term, the derivative of a logarithm means we flip over the argument. And then we have to do the chain rule to say, okay, what was the derivative of the inside? The derivative inside with respect to T is just going to be Boltzmann's constant over Hc. And then we can see that we can cancel those bits, cancel Boltzmann's constant. We're just left with 1 over T there. Now we take the derivative of this with respect to T, And because we have a t in the bottom, the derivative of this is just going to be delta H double dagger over RT squared. We have to change the sign here. Take the derivative of this with respect to t. Oh, as long as delta H double dagger and delta S double dagger, well, as long as this is constant, this is just going to be 0. So we have this simple expression, which is, once we've canceled everything here, this is just 1 over t plus delta H double dagger over R. So if we want to, we can say that that is equal to EA over RT squared. So EA over RT squared must be equal to 1 over t plus delta H double dagger over R. Oh, I left a factor of t squared off here. Let's put a t squared here. So we have a t squared here. So we have EA over t squared. It's going to be equal to R over t plus delta H double dagger over t squared. Then we can multiply both sides by t squared. Actually, let's just go to the next page on that. So we get EA is equal to RT plus delta H double dagger. Or finally, delta H double dagger is equal to EA minus RT. And this is for the simple case study of a bimolecular solution phase reaction. So let's go back and do an example specifically of that SN2 reaction. So we've got ethyl bromide plus hydroxide in that substitution reaction to give us ethyl alcohol plus bromide. So if we look up the activation energy for this, we could see, or we could do some temperature dependent experiments and just measure it ourselves. It's 89.5 kilojoules per mole. So at room temperature, this is going to be that minus R times T, or about 87 kilojoules per mole. So we can see that the activation enthalpy is different from the activation energy, but they're the same order of magnitude.